So we've talked about a number of ways in which we can determine or calculate mechanical properties, but I want to talk about one more factor having to do with how it's used in the design process, and that's the safety factor. So obviously, whenever we test something like mechanical properties, there's going to be variability in the tested properties, and that's from uncertainty, right? And that can come from a number of places, either measurements that you take with calipers, uncertainty in the instrument itself and various components, and so forth. And so we're always going to have variability, and obviously, we don't want that to affect the design process, right? So if we know the yield strength is a certain value, or if we have the yield strength as a certain value, right, there's going to be some variability amongst the material and the way we test it. And so we don't want that to affect the design process. So if we don't want it to plastically deform, right, which is what the yield strength tells us, then we might want to go a little bit lower than the yield strength, not right at the yield strength, because if there's variability or uncertainty in that number, then we could possibly introduce plastic deformation. And so when we test the properties, we always want to look at this variability. And so the most straightforward way statistics would be to look at Gaussian statistics and look at averages and standard deviations for these values, right? So I put the average here. You're all probably familiar with how to calculate an average. And there's also how to calculate the standard deviation of that. And that tells us about the statistics and of these numbers. And therefore, this is something that we're going to need in the design process. So to kind of overcome that uncertainty, because again, we don't want to sort of push it to its limits, right? If you're making a car or something where human life is involved, for instance, right? If that car would break down at a certain value, you don't want to push it directly to that value. You want to have some um, factor of safety, is what we call it, and so that's what we introduce for stress in these cases. And so the factor of safety N is introduced. So, for example, if we don't want yielding or plastic deformation to occur, then we have the yield strength, and we divide by a factor of safety to arrive at a working stress that is safe to push this material to. And this factor of safety is going to be some number, usually between 1.2 and 4, but that factor would obviously um, change based on what your design criteria is, right? So a large factor of safety is required if the failure would be what we call catastrophic, right? So a loss of life, damage to property, things like that, houses, cars, space shuttles, things like that. And then small factors of safety would be used to basically just get us close enough, right? And when catastrophic failure isn't an issue, and when over designing it could cause it to become more costly. So these would be things that aren't, catastrophic, where if there's a failure, then it doesn't really matter. The example I always give for this is chalk, right? If you're writing on the chalkboard, like we normally would do for this class, something like that, right? If I'm writing on the chalkboard with the chalk, if the chalk breaks in half, nobody dies. So we don't really need to over design that system. Sure, I would like to have stronger chalk, but I also don't want it to cost $20 a stick. So that's the kind of example here for small factors of safety. Whereas if you're designing a part for a space shuttle with humans inside of it, right, you want a pretty large factor of safety, because we don't want anything happening that would cause a catastrophic failure. So those are kind of the two extremes that we have. So I think the easiest way to kind of get a view of this safety factor is for us to look at an example. So let's go ahead and look at an example regarding this factor of safety. All right, so let's take a look at an example regarding the safety factor. So let's say that we want to calculate the diameter d necessary to ensure that yield or yielding does not occur in a steel 1045 carbon steel rod. And then we have the force of 220,000 newtons applied, and we're going to use a safety factor of 4. So here, instead of having to look up the values in the textbook, I'm going to go ahead and give you for 1045 plain carbon steel. Keep in mind, though, a lot of these values you can find in our textbook. So for that material, again, we have a diameter D and then a length L naught. And our yield strength and tensile strength are given here. So see if you can calculate the diameter necessary so that it doesn't yield when the force is applied of 220,000 newtons. So see if you can do that. Pause the video real quick and then come back and we'll work this one together. All right, so let's take a look at this example again, and we're trying to find or calculate the diameter. We have a safety factor of 5. We know the force applied. And so the first thing that you should keep in mind with this type of question is we're given force, right? But we're talking about yielding and yield strength. And so we need a stress value. And so we can calculate the stress for this value. And that would obviously depend on the area, the cross-sectional area, which would have diameter. So if we want to set this up, that's what we're going to do, right? We apply a force, and we also know our working stress is going to be, if we don't want it to yield, is going to be yield strength divided by the safety factor. We can plug in the value for the yield strength from what we know about 1045 plain carbon steel. We know the safety factor is 5, and for the working stress, we know the force, but we're trying to figure out the diameter. And so from there, we can basically plug in the force, plug in the area equation with D as our unknown. And so with D as our unknown, we can rearrange and solve for D, and that gives us a value, which if we're doing this in terms of newtons and meters, this would also have to be in pascals. So we have megapascal, so keep in mind the units there. And so when we do that, we get 0.067 meters, which is 6.7 centimeters. So what does this say about what we're asking here? So it says that if we want, let me go back to the problem statement here. What that's saying is that if we want to apply this level of force to this part, and we're going to have a safety factor of 5, and this is going to be made out of 1045 steel, which has a yield strength of this, then our material has to be at least have a diameter of 6.7 centimeters based on our calculation for it to withstand those parameters, those design parameters. So it has to be 6.7 centimeters or greater to sustain that. Anything below that would be within the not within the factor of safety, and therefore it could yield in under those situations. So this is how we're designing it so that it does not yield under that applied force. So that's the kind of question that we tend to ask with this safety factor, is something to do with, you know, a design of a part and the forces and stresses on that, and how do we build that so that it's safe to operate, it doesn't yield, for example, which would involve the yield strength.